Welcome back, students. In this video, we're going to look at alkyne hydration, which is where you add an H and an OH across your triple bond. Before we get started with alkynes, let's remind ourselves what we saw with alkenes. With alkenes, we utilized H3O+, which is our acid, to get OH to the more substituted position. So this was a Markov-Nikov addition because that OH went to the more substituted side. But what's going to happen if we start with an alkyne instead of an alkene? Well, the same type of thing is going to happen. You're going to add an H and an OH across the pi bond. The difference is going to be that you still have a pi bond at the end because only one of those pi bonds is going to react. So we have our 3 carbons. We still are going to have a pi bond here. And remember, your OH still goes to the more substituted side because this is a Markov-Nikov addition. That means you get an OH at this position. This thing has a name. It's called an enol. An enol, you say, what's that? Well, it's an alkene and an alcohol. And here's the thing with the enol. The OH of the alcohol has to be bound to an sp2 hybridized carbon, right? It has to be on the alkene carbon. So we call this an enol. En for alkene and all for alcohol. One other thing that we need to note is that for acid catalyzed hydration of alkynes, just adding H3O+ isn't enough. You're actually going to also see a mercury sulfate compound because that's going to be a secondary catalyst that we're going to use to force this reaction to occur. Now, those enols are special. They don't stick around that way. You can't isolate them. Let's talk about what they do. Enols do something called tautomerization, or enols tautomerize, and you can't stop it from happening. That enol in the presence of any little bit of acid or base is going to tautomerize. Now notice you added acid purposefully in this reaction, so there is absolutely acid for this enol to use as its catalyst to tautomerize. Let's look at the mechanism on how that tautomerization is going to happen. Even though this can happen via base as well, because we have acid in the flask, we're going to focus on the acid catalyzation of this tautomerization. The first thing that's going to happen in the tautomerization is your pi bond is going to come over and abstract a proton. When your pi bond abstracts a proton, now that proton is going to be added here, and you already have that OH present. Well, why are we adding the proton there? Because wherever the proton did not add is where a positive charge is. And the positive charge is going to be more stable if it is secondary. Now, if we look at this structure, this has a resonance structure. So I'm going to change my arrow to green to illustrate that I'm talking about resonance now. So I can bring this arrow around to show that there are 2 resonance structures for this compound, and they look like this. If you wanted, you can continue to draw that hydrogen in green that I drew in, but you don't really have to. Now, when you pulled off the proton at the beginning from H3O+, you left water. Remember, this is acid catalyzed, meaning you have to recreate acid at the end. So you have water, and that water is going to come in, pull off this proton so that you can end up getting H3O+ regenerated. It's always such a good feeling when your mechanism successfully regenerates your catalyst. Keep in mind, this is an equilibrium reaction, so I'm going to draw my other arrow that way as well. It's just that the ketone is much more highly favored in the equilibrium than the enol. Let's consider what you're going to draw for the overall reaction. You're not going to draw your enol as your final product because enols tautomerize so rapidly. We don't even draw them as the final product. If you want to draw them on a scrap sheet of paper because it helps you predict what your final product is, go for it. But it is not your final product. What you're going to do is you're going to find your alkyne in your structure. When you find your alkyne in your structure, if there's a more substituted side, like there is here, that's where your OH is going to go. That OH eventually turns into a ketone. So your final compound is this. Let's try it again. I'm going to look at my triple bond. Here is the location of my more substituted side. That's where your OH goes. Where the OH ends up is where your C double bond O is going to be. So let's draw the rest of our carbon structure, making sure not to lose any carbons, right? That's easy to do. 1, 2, 3, 4. And that's not nomenclature numbering. That's just me trying to keep track of things. 1, 2, 3, 4. Good. And at the third position, you have your double bond to oxygen. All right, so let's reiterate. You're finding your triple bond. Once you find your triple bond, you find the more substituted side. Where your more substituted side is where your C double bond O is going to go. Now this one, there's not a more substituted side. So what happens? Well, you get a mixture of products. And it's going to stink, but it's going to happen. So you are going to have a C double bond O here, and you're also going to have another product where your C double bond O is here. So let's go ahead and draw those. I want to count my carbons really quick to make sure I don't lose any. So I've got 1, 2, 3, 4, 5, 6, 7. So I'm going to just go ahead and draw 7 carbons. 1, 2, 3, 4, 5, 6, 7. And I'm going to count that again. 1, 2, 3, 4, 5, 6, 7. And if we're counting from the right, and this one could be nomenclature numbering, at the fourth position, you're going to get your C double bond O. And then you're going to have another product where at the third position, you'll get your C double bond O. So if you don't have a terminal alkyne, so if your alkyne is not terminal, you need to be prepared to end up with a mixture of products. Let's wrap up. In this video, we looked at acid catalyzed hydration of alkynes, where we considered that H and OH are going to add across one of the pi bonds of the alkyne, and you form an enol. Enols are not very stable. They're going to tautomerize immediately into, in this case, a ketone, and you're going to get a ketone as your final product. Make sure that you're watching out for the possibility of a mixture of products if you have an internal alkyne. So an alkyne where the triple bond is sandwiched on either side by more carbons. Thanks so much for your attention. This is Katoni signing out.